Welcome to lecture 26, change of basis, linear mapping, changing the basis. So we're going to discuss a linear mapping between two vector spaces. We're going to have a vector space U, which has a dimension of n, and a vector space V, which has a dimension of m. And the mapping, which we're going to call F, is going to be linear, which means if I look at F acting on the sum of two vectors, AU1 plus BU2, it equals A times F of U1 plus B times F of U2. And whenever we have a mapping that satisfies that property, it's called a linear map. You can see here on the picture on the left, this particular mapping is mapping two objects from the space U to one object in the space V. And so this would be a mapping that is not invertible, which means I cannot go from V back to U because I don't know which of those two objects I'm supposed to go back to. And so the way that we determine whether or not a mapping is invertible is we look at the null space. The null space is the set of vectors in U that map to the zero vector in V. If that null space has only one element, then the mapping is invertible, and we can go backwards from V to U. We're going to use a matrix to represent this transformation, F from U to V, and because of the linearity property, we can determine this mapping for any vector in U if we can determine it for the n orthonormal basis vectors in U, which we denote E sub j of U hat, with j going from 1 to n, in terms of the m orthonormal basis vectors for V, which are denoted E sub I V hat, I equals 1 to m. Each one of those vectors is normalized, so the scalar product of the vector with itself is equal to 1. And the scalar product of each vector in the U subspace with any one of the other basis vectors in the U subspace is equal to 0. That tells me that they are orthogonal, and similarly for the vectors in the V space. Then what we do is we're going to use this matrix that we call Mij. It's just a set of numbers, and it's going to satisfy F acting on Ej is equal to the sum I equals 1 to n Ei V hat Mij. Now that might look a little bit odd to you, but you'll see that is exactly the order that we want. The I index is running over the rows. There are m rows to this matrix, and the j index is running over the columns. There are n columns to this matrix. In this particular case, we picked n bigger than m. All right, let's move on. What we're going to do is we're going to write our vector U as equal to U1 E1 plus U2 E2 all the way out to UN En. That is just writing an arbitrary vector U in terms of its coordinates with respect to the basis that we've chosen for U. And then F of U, by using the linearity property, is going to equal U1 times F of E1U plus U2 F of E2U plus all the way out to UN F of EUN hat. But we know what F of each of those basis vectors are. It's the sum I equals 1 to m EVI of Mij. So I just take that object, multiply it by the Uj, which is the factor that's coming out in front, and then sum that from j equals 1 to n, and I'm going to get what f of u is. And we're going to schematically write that as the sum I equals 1 to m of vi times ei v hat. And we're also going to use the notation that you're familiar with. M times the vector u is equal to a vector v. Now schematically, if you look on the left-hand side, you can see what we have here is a vector in u has a dimension n, so it's that long, skinny rectangle. I multiply it by the matrix M. Because the matrix is a rectangular matrix, I end up with a matrix that has a dimension little m, and that is, of course, a vector that sits in the vector space V. And so you can see schematically how this matrix multiplication is going to work. Okay, the inverse transformation, if it exists, is going to be denoted by M inverse, M superscript minus 1. For the inverse to exist, we're going to have m equals n, so they'll always be square matrices when we have an inverse. Okay, let's look now at changing the basis of this transformation. So suppose we want to change the basis in U from E hat JU to E hat JU prime. Now, both of them are orthonormal bases, but the different basis vectors from the unprimed to the primed space do not need to be orthonormal to one another. We're going to call the transformation matrix that transforms U into U. We're going to call that matrix P. It is a linear mapping, so there is a matrix that will do that. And this mapping, because it goes from U to U, is going to be a square matrix. We're going to similarly transform the basis in V from E V hat to E V hat prime. And we're going to call that transformation matrix Q. That's also a square matrix. It's a dimension m by m matrix. And because of the properties of orthonormal bases, it will turn out that both of these maps are invertible. So I can talk about a P inverse, and I can talk about a Q inverse. So if we have a vector U, which is written as U1, U2, all the way out to UN in the old coordinate basis, it will be called U prime, U1 prime, U2 prime, all the way out to UN prime in the new basis. And what we find is U prime will equal P times U. Or if you like, U is equal to P inverse times U prime. And then similarly, the same thing happens in the V vector space. So V prime is equal to QV, or V is equal to Q inverse V prime. And now we can use those different results, those different identities, to determine how the matrix M transforms when we have this basis change. So if M was the original transformation from U to V, we want to figure out how does it change when this basis changes. So what we do is we start with V. V is of course equal to Q inverse times V prime. That's essentially the definition of Q. And we're going to say as well that V is equal to M times U, because that is the initial transformation from U to V. I'm going to rewrite U as P inverse U prime. And then I'm going to multiply both sides by Q, so I'll get V prime is equal to Q M P inverse acting on U prime. I'm going to call that net matrix M prime acting on U prime. And we learn that M prime is equal to Q times M times P inverse. And that would be the way in which we do a coordinate change or a basis change on both of the vector subspaces, and we want to know how does the matrix change that defines the map between those two subspaces. All right, we're going to find a very interesting case is going to occur when the vector spaces are identical. V is equal to U. Then P is going to equal Q, and we'll have M prime equals P M P inverse. And whenever you have that particular case where the matrix is the same on both sides with a P and a P inverse, that is called a similarity transformation. And in this case, we would say M is similar to M prime. That's the way that we would state that we have a similarity transformation between the two matrices. All right, let's look at the properties of these similarity transformations. The first one is if A is similar to B and B is similar to C, then A is similar to C. Let's see how we prove that. Well, we have A is equal to P, B, P inverse because A is similar to B. Similarly, B is equal to Q, C, Q inverse because C is similar to B. And so now we just write out A. A is P times Q times C times Q inverse times P inverse. And I want to verify for you that that is equal to the matrix PQ times C times PQ inverse. And this occurs because PQ inverse is equal to Q inverse P inverse. But you might not know that because we haven't verified it. So let's go ahead and prove that PQ quantity inverse is equal to Q inverse P inverse. Note that I have to interchange the order when I take the inverse of a product of two matrices. So let's check. Well, PQ times PQ inverse is equal to the identity. That's the definition of it. So I'm going to now look at PQ as the matrix P times the matrix Q times the matrix PQ quantity inverse. And I'm going to multiply on the left by P inverse. Then I get P inverse is equal to Q times PQ quantity inverse. And I'm going to multiply by Q inverse. And I'm going to get Q inverse P inverse is equal to Q inverse Q times PQ quantity inverse. And that's equal to PQ quantity inverse, which is what we wanted to show. So we've proven the first thing. If A is similar to B and B is similar to C, then A is similar to C. That's the transitive property. And this fact is an important one to remember about similarity transformations, but also this product result for the inverses is a really important one for you to remember. That when I have the product of two matrices, when I take the inverse, I have to invert the product of the inverse matrices to get the inverse of the product. Okay, if A and B are similar, then the determinant of A is equal to the determinant of B. Now this follows from the fact that the determinant of the product of two matrices is the product of the determinants. We established that when we were talking about determinants. Now since I is equal to PP inverse, that implies the determinant of I, the identity matrix, which is 1, is equal to the determinant of PP inverse, but that's equal to the determinant of P times the determinant of P inverse. And now we just divide both sides by determinant of P. We find the determinant of P inverse is 1 over the determinant of P, which then tells us if the determinant of A is equal to PB P inverse, then we have determinant of A is equal to determinant of PB P inverse, which is determinant of P times determinant of B times determinant of P inverse. But you see determinant of P times determinant of P inverse, that's equal to 1. So it's just left with determinant of B, and that's indeed what we wanted to show, that when you do a similarity transformation, you don't change the determinant. Now our third property is if A and B are similar, then A to the K raised to the kth power is similar to B raised to the kth power. So here's the proof. We write A to the K as a product of K terms, A times A times A, all the way out to K repetitions of A. We then replace A by its similarity transformation, PB P inverse, everywhere. Now we notice that all of the internal cases, we always have a P inverse next to a P, and I can replace the P inverse P by the identity matrix. So I get P times B times I times B times I. K repeats of that times I times B times P inverse. Now, of course, B times I times B, that's just equal to B squared, and you find that all of the I's are going to get rid of, and I'm left with P, B to the K, P inverse, but that indeed is the similarity relationship between A to the K and B to the K, so we've proven this third result. Now when the vector space is real, this transformation matrix is orthogonal, which means P inverse is equal to P transpose. When the vector space is complex, this transformation matrix is unitary, which means P inverse is equal to P dagger, where P dagger is called the Hermitian conjugate, and to get that we transpose the matrix and we do a complex conjugation. So that means we do a complex conjugate of every term. You can think of an orthogonal matrix as a Hermitian conjugate as well, but because every element of the orthogonal matrix is real, the Hermitian conjugation doesn't do any. The conjugation part, complex conjugation part, doesn't do anything. Also remember the transpose of a matrix Mij is just Mji. I simply interchange the rows with the columns of the matrix. And when the matrix is square, it's still the same kind of matrix when I do the transpose. And all of these different transformation matrices are always square. Okay, that's all that we have for this lecture.